Welcome to this lecture in which we elaborate on the PDO process that has been partly designed in the previous lecture. Initial choices for main steps AE have been suggested and these have been put together here. The process configuration resembles the main steps such as described in a patent by one of the leading PDO manufacturers. Now we will elaborate a bit on the mass balances for these steps. Assuming that all cells are retained by microfiltration, we still cannot remove all liquid from them. We assume that microfiltration can reach 120 gram dry mass per kilogram. Be aware that this corresponds to 480 grams of wet cell mass per kilogram when we account for intracellular liquid. The 520 gram extracellular liquid may be just enough to keep things flowing, and in the mass balance shown, it is assumed for simplicity that the water and all solutes distribute evenly between intracellular and extracellular liquid, which is probably true for PDO at least. In this way, 41% of the PDO would be lost with the removed cells if these wouldn't be washed by diafiltration. Countercurrent diafiltration in 3 stages is useful for washing the retentate from microfiltration, which is the feed here. Water is the wash liquid. Gradually, the cell suspension gets depleted from solutes. On the other hand, the wash water becomes more concentrated in solutes in each next permeate. For recovering 90% PDO that would be lost with cells, so not removing 10% from the microfiltration retentate, we can use the Kramser equation to calculate that we need a separation factor of 1.66. The equilibrium constant is a bit higher than 1 because we take the whole retentate flow, including dry cell mass that is excluded from partitioning. Knowing S, FL and K, we can calculate FV, which tells us how much wash water is required. The actual calculation involves an iteration as shown in a downloadable Excel file. Using more wash water will recover more PDO, but that leads to more water to be evaporated later. At this point, we cannot determine the trade-off. Filtered broth and diafiltration permeate are jointly sent to ultrafiltration. There we assume complete biopolymer removal, which is optimistic. They stay in the retentate as concentrated aqueous solution. We assume 50 grams biopolymers per kilogram retentate. The other compounds are assumed to freely pass the membrane but will not completely permeate, to keep 950 grams of other compounds per kilogram retentate. Cation exchange and anion exchange will exist of a series of batch-wise steps. After sending the feed over a column with cation exchange resin in the H+ form, the column needs to be rinsed, regenerated with HCl solution, and rinsed again. Continuous processing needs at least 2 cation exchange trains that operate alternately. After cation exchange, anion exchange is done in an analogous way, but using a column with an anion exchange resin in the OH- form and with sodium hydroxide solution for regeneration. Designing all these steps involves a lot of choices, and therefore only an approximate overall mass balance is shown here. Evaporation is assumed to be done as suggested in the previous lecture, using 3 effects and mechanical vapor recompression. For now, we assume that 95% of the water is evaporated with only 0.5% PDO loss. We might need 1/3 kilogram of steam per kilogram of water evaporated. Per kilogram of PDO, that will lead to substantial steam costs. To design the distillation train, we would have to specify the organics in detail and their volatilities. Then computation of distillation can be done using complicated but well-developed and reliable methods. For now, we first distill PDO over the top to remove higher boiling components, and we then distill out lower boiling components. We hope that no close boiling impurities were around or have been formed by degradation during distillation. Without performing detailed design, we can still guess split factors per distillation and review the mass balances that we obtain. Now we have mass balances for all DSP units. You can download the Excel file from our course website to get a better understanding of the previous slides. To simplify further analysis, we now merge all DSP units in one DSP block. From the overall mass balance of the DSP, we see that we have reached the required PDO specification. We can also calculate the recovery yield, which is 92% of the PDO in the broth. That is quite reasonable, but the 8% loss will have implications for the overall production costs. For example, per kilogram pure PDO, we must allocate 8% extra fermentation capacity to account for this, while fermentation equipment is typically a major cost source. Moreover, the 8% loss also leads to 8% extra glucose costs, and the lost PDO leads to extra waste treatment costs. We have not yet introduced much auxiliary chemicals, almost only water. The generated waste is also mostly water, and half of it originates from the fermentation. For obtaining the DSP cost, we can use the mass balances to quickly estimate the costs for energy, auxiliary chemicals, and waste treatment once we know prices per item. For the consumables, we need to know their replacement frequency. This depends on fouling and needs experimentation. First guess would be 1 replacement per year. The amounts required depend on the capacity. The Excel file shows estimations that lead to the numbers given here. We cannot yet say much about DSP equipment cost, but the aerobic fermentation equipment for PDO might easily dominate the overall equipment costs. Looking back at the design recipe ingredients, we can see we have used mass balances for each unit operation and have partly used phase equilibrium. The next steps are beyond the contents of this course, so we have not yet determined equipment dimensions and detailed energy requirements. From the simplified PDO case, we have learned that DSP is challenging. It involves a lot of different operations. Each of those has numerous design options. Typically, alternatives would need to be compared on recovery yield, energy use, equipment requirements, etc. This requires process assessment, such as elaborated in the later week of this MOOC, and iterations. However, considering the number of DSP options, it may be impossible to find the best option. A better strategy is to develop a good enough option in which DSP is not the bottleneck of the overall process. This was DSP in a nutshell. Thank you for attending.